Okay, so now we are going to use the concepts about Newton's first and second law that we learned in previous video and apply it to a situation where objects are falling down, or let's say they're thrown up and then they're going up and then coming down back to the ground. Um, how would these objects move, and how can we explain their motion using forces? So that's where we are going to use Newton's laws and try to understand their motion. So right now the case that we are looking at is free fall, but it's without air resistance. There is no air resistance acting on it. And right out of the way, we need to understand what are those situations where air resistance will not act. Mostly, you can think of those situations where there is a vacuum. So when there is a vacuum, then you may have no air resistance, or you may drop something from a small height. And by a small height, I usually mean that, let's say, you drop a pencil from your hand or a ball from your hand. Those you would consider examples to be small heights. Okay, but it also depends on the kind of object that you're dropping, because you probably know from experience that if you have a feather in your hand or a paper in your hand and then you drop it from a small height from your hand, it doesn't really fall as quickly as the pencil or the ball, because air resistance then does come into action. So this case is not for very light objects like feather or paper, etc. So with this out of the way, we have now understood what kind of situations occur where air resistance is not acting. But now we need to understand what are the forces that are acting on the object when it's falling down. So think of this feather on the left, on the hammer on the right. If I ask you which force is acting on these two objects, what would you say? Well, the obvious answer should be the weight of the feather. Weight of the feather. And in this case, it would be the weight of the hammer. And we know pretty well that the weight of the feather is much less compared to the weight of the hammer. So what do we expect if there is total vacuum right now and there is no air resistance, and only in the presence of the weight, which object would fall to the ground quicker? Would it be the hammer or would it be the feather? Think about this for a moment, and then we can start explaining and try and explore what is actually going to happen. So the same question was posed by Galileo as well many years ago, and he came to the conclusion that when there is no air resistance, when it's the only the weight acting on the object, this is the only force present. All objects, no matter how heavy or how big or how small they are, they will all fall in the same manner to the ground at the same speed with the same acceleration, and they will fall together if dropped from the same height. Now, how can we explain this? Well, let me try and explain this to you with a formula that we have already learned. So you know that resultant force is equals to mass times acceleration. And for this feather or the hammer, we know that the force that is acting on them is their weight. So the only force acting on them is their weight, which means we can say that it's the weight equals mass times acceleration. Now, remember what is the equation of the weight, or how do you find the weight of any object? Well, it turns out that the weight is equal to mg. We have learned this equation in the lecture named Types of Forces, and you can go and watch that video to remember the formula for the weight. Now since mg is equal to ma, what happens? Mass and mass gets divided and it gets cancelled out. So what we get here in the end is that the acceleration of free fall when it's only the weight acting on the object will be equal to the gravitational field strength on that planet. Now we know that for Earth this value is around 10. So we can say safely when you are dropping objects on Earth or near the surface of the Earth, their acceleration of free fall will be equal to the gravitational field strength, which is equal to 10. So I can say that acceleration of free fall equals strength of gravity. So A equals G equals 10 meters per second squared. Alright then. We now know that the acceleration of all objects, no matter what is their mass, since mass is cancelled out in the equation, no matter what is the mass of the object, no matter what is the size of the object, it doesn't matter. Every object when free falling near the earth will have the same acceleration, 10 meters per second squared. Now let's look at the feather, for example, or the hammer. We can draw them at different positions. So when you draw them initially, let's say we call this time t equals to 0 seconds. They will be both at rest. Their speed will be equal to 0 meters per second. And it's the weight which is acting on them. Now we know from the above equation that their acceleration is going to be 10 meters per second squared. So what would be their speed after 1 second? Can you take a guess? Well, by definition of acceleration, it is the speed or the change in speed over 1 second. So over 1 second, the speed of both these objects should become from 0 to 10. It should increase by 10 meters per second. So if I try to figure out the speed of the feather here, it should be 10 meters per second. And for the hammer as well, let's just draw it as a dot. It will be 10 meters per second. What would be the speed of the feather after 2 seconds? Well, 1 more second has passed, so we can be pretty sure that the acceleration is still the same, since it's the same force acting on the feather, which is its weight, and for the hammer as well, which is the weight of the hammer. So the acceleration will stay the same. Nothing has changed. It's the same acceleration. So the change in velocity for the next second should also be the same. So speed after 1 more second will become 20 meters per second. And same goes for the hammer. It will also be 20 meters per second. Or any other object which is falling near the earth without air resistance will have these same speeds. And you can notice that the gap that I have drawn between 0 and 1 seconds and 1 to 2 seconds is larger. Why? Because the average speed in the first second and average speed from 1 to 2 seconds is different. Now it has sped up more. So because it has more average speed, it covers more distance. What is going to happen after 3 seconds? Well, after 3 seconds, it will cover even more distance. And again, the velocity is going to increase by 10 more. So this is going to become 30 meters per second. And this is also for the hammer going to be 30 meters per second. And again, this is happening because the weight of the feather has not changed. It's still the same force. So since the resultant force is the same, nothing is going to happen to the acceleration as well. It's also going to stay the same. And they are going to keep accelerating unless they hit the ground. And each second, their speed is going to increase by 10 meters per second. And this acceleration will always stay the same unless some other force appears or something try to stop them, or they just hit the ground. Well, now from this we can basically conclude that when weight is the only force acting on falling objects, we can say that their acceleration is 10 meters per second squared near Earth. For other planets, or moons or stars, it will be equal to their strength of gravity. So for example, on the moon, the strength of gravity is 1.6 newtons per kilogram. So there the acceleration is going to be 1.6 and not 10 like Earth. And for Sun it is much more than Earth, so the acceleration will be much more than 10. The value of 10 is only true for the objects falling near Earth. For other planets, this value is going to be different. For Mars, for Venus, for Saturn, for Jupiter, all have different values of g, so you will get a different value of acceleration of free fall. Okay, what else can we say? We can say that acceleration is uniform. Acceleration is uniform, so it does not change. And you know that when acceleration is uniform, it stays the same. It means that the acceleration is not going to change. So you can think of the speed time graph or the velocity time graph that we will end up getting for objects that are falling without air resistance. Think about that, and we are going to sketch it in a while now. Size of acceleration does not depend on their mass or shape or size, because these things are not part of the equation which basically told us that A is going to be equal to G, and we saw that mass got cancelled out. So size, density, shape, nothing matters, or not even the mass. So no matter you're drawing all objects which are heavy or light or different shapes and sizes, they are just going to drop with the same acceleration, and they're all going to speed up together and hit the ground together if they are dropped from the same height. So now let's think about the speed time graph or the velocity time graph when an object is dropped like this. Obviously it's going to start at 0, and since the acceleration is 10, the gradient of this graph should be equal to 10, and what we will end up with is a straight line like this. When an object is dropped like this, this is what the graph of speed or velocity against time is going to look like. If you find the gradient of this graph, it will be equal to the value of g, and this value is obviously 10 meters per second squared on Earth. And just to reiterate, for other planets it will be different, but no matter how heavy or light the object is, you are always going to get the same line. And if I were to draw some values on this graph, what we are going to get is after 1 second the velocity will be 10, and after 2 seconds the velocity will be, I don't know, well, let me change it up a little bit. Let's say after 1 second the velocity will be 10, After 2 seconds, the velocity will be 20. After 3 seconds, the velocity will be 30, and so on and so forth. So this will be the graph. But what changes will occur to this graph if the same thing was done on the moon, let's say. So if I draw a graph for a similar situation, but this time it occurs on the moon. Well, moon has a gravity which is weaker. So what you are going to get is a very similar shape of the graph if you drop the same object, but the only thing different will be that the acceleration is going to be much smaller. So it's still going to be uniform acceleration. They're still going to accelerate, they're going to speed up, but they're not going to speed up as much. And this is the type of graph that we are going to get on the moon. And you can see that the slope of this graph, the gradient of this graph, is much smaller than the graph for Earth. Also think about what would be the shape of distance time graph or displacement time graph for any object which is dropped on any planet. Let's just try and understand the general shape of this graph. So if I say displacement versus time, now let's imagine you are measuring the displacement from the point where you dropped the object. So if you drop the object from the top of a building and you are measuring, or the roof of your house, and you are measuring the displacement from that point where you dropped the object, what would be the shape of the graph? Well, you should remember that the gradient of this displacement time graph should be equal to the magnitude of the velocity or the speed time graph. So since the velocity in the beginning is 0, our graph should also have a gradient which will be 0. So our graph, if you notice carefully, starts with a slope which is basically non-existent. The graph is initially very flat, and as we go on, the graph becomes steeper and steeper and steeper and steeper, and this is going to keep happening. The graph is going to stay a curve, and it will just keep increasing in gradient because the velocity keeps increasing. So this is what the shape of the graph would be on Earth if you were to draw a graph of displacement versus time. But what happens if I try to draw a graph of height? Let's say if I'm drawing now a graph of height of the object from the ground. So let's say this is my building, this is the building, and this is the ground, and this is a ball that I dropped from the top, and what I'm trying to measure is the height of the object from the ground. So what kind of graph would I end up with? Well, this time around the shape is very much the same. The only thing different would be that the height will start from a maximum value, and then it will decrease to 0 as the ball comes and hits the ground. So again, I have to be careful. At the beginning of the graph, the shape must be such that it starts out as a flat line, and then the gradient keeps increasing and increasing, and then it hits the ground. This is the point where the ball has hit the ground. But you can see that in the beginning the graph is a flat line because initially the velocity was 0. Now I also want to go over one more example which is quite common, where let's think about throwing a ball up in the air, okay, and then watching it come back to the ground. So let's say you are on top, you're standing on the roof of a building, you have a ball in your hand and you throw it up. So this is the ball that you throw up. Obviously the ball is going to go up, so the ball goes up and then it starts to come down, and let's say you let it fall to the ground, and this is where the ground is, and the ball comes and hits the ground. Let's try and understand what would happen to the ball while it's going up and what would happen to the ball while it's coming back down. Well, when the ball is in this position, when the ball is going up, what are the forces acting on the ball? This is a very important question. Well, the force on the ball is just its weight. And since the weight is downwards, the acceleration also has to be downwards. And the ball is traveling upwards. Therefore, we must conclude that the ball is going to decelerate in this part of the journey. The ball is going to decelerate. And the deceleration will have the value of 10 meters per second squared. So the velocity will be maximum. Let's say you threw the ball with a velocity of 20 and it will be a maximum in the beginning. Now right when it reaches the top, right when it reaches this point, the ball is actually going to be stationary for a while. So at this point the ball becomes stationary. So it is at rest for a moment, or just for a brief moment, and then the ball starts to come down. Now let's think about the ball on its way down. When the ball is on its way down, again it's the same force of the weight acting on the ball. And since the ball is moving down and the force is also in that same direction, therefore the acceleration will also be downwards. So since the velocity and acceleration are in the same direction, we can conclude that the ball is actually accelerating now. And that acceleration will have a value of again 10 meters per second squared. So initially when the ball goes up, it slows down and then it has a speed of 0, and then the ball moves in the opposite direction and then the speed increases or the velocity increases, but remember it increases in the opposite direction. So from what we know about velocity time graphs or speed time graphs, can we draw a graph for this situation? Let's say we threw the ball at a speed of 20 meters per second. Now we know that the speed is going to decrease and it's going to become 0 at some time. So if the acceleration of the ball or the deceleration of the ball is 10, then we must know that it should come to rest in 2 seconds, or it should go to the highest point in 2 seconds. That's why the graph is actually going to be a straight line. And why do I know that it's going to be a straight line? Because it's a case of uniform acceleration. The acceleration does not change throughout this journey. So this is what the graph looks like for the ball being released. This is where the ball was thrown up. This is when the ball is at its highest position. And remember, this is a velocity time graph. So this is the ball at the highest point. Now think about what happens from here onwards. Now the ball falls down and the ball's velocity is in the opposite direction. So we must draw it as a negative value on the graph. So the ball's velocity increases but in the negative direction, and sure enough this is what's going to happen, and the acceleration has the same value. It's just that the ball is now going to speed up since the velocity is in the opposite direction. So what happens is the ball comes down and it accelerates. So the gradient of the graph does not change because the acceleration does have the same value. Now what is so special about this time of 4 seconds? Well, this is the time when the ball is passing right in front of the person who threw the ball. It's right at the same height from where it was thrown. So it's passing the roof of the building, and assuming that the ball is allowed to fall down to the ground, the ball is going to keep traveling towards the ground with the same acceleration, and the velocity is going to keep increasing, and we can continue that graph as a straight line graph unless it hits the ground, and then it's gonna bounce, or it's maybe just going to go into soft ground and stop. But this is what the graph of velocity versus time would look like. Alright, I'll see you in the next video.